This is the 11th video on a series about complex arithmetic methods and geometric interpretations with Mathematica. My name is Bill Kinney. In the last video we started to introduce the idea of complex division by first of all thinking what it would mean for a complex number to have a multiplicative inverse or reciprocal, what it would mean for a plus bi to have a number x plus yi such that when you multiply them you would get the multiplicative identity 1. We saw that it resulted in a system of linear equations that, under the assumption that a is non-zero, we could solve to get this. Turns out if b is non-zero, you could also solve to get this, and the only way you can't solve for this if both a and b are 0. We then saw that that means there is a formula for the reciprocal of any complex number, and therefore if we want to do complex division, for example, taking z1, which is 5 plus 7i, and dividing by z3 here, which was 2 plus 3i, that we could think of it as finding the reciprocal of z3, the multiplicative inverse, and multiplying it times z1 to get the answer. What I want to show you in this video is there's another way to do it that avoids having to use this formula all the time. And it's based on the idea that if you multiply a complex number like 2 plus 3i times its reflection across the real axis, in this case that would be 2 minus 3i, trying to get it as close as I can here, that you would get, first of all, a real number because their arguments will be opposites of each other, and secondly, it's actually a special real number. The length of this is going to be the product of the lengths of these two things, and what that's going to mean is that the real number that you get out is going to be a squared plus b squared if you think of the real and imaginary parts of this beginning complex number as a plus b, a and b. This complex number is a plus bi. This complex number down here is a minus bi. That's called the complex conjugate of a plus bi. There's a special notation for it. I'll put it down here. Complex conjugate. If we are given a complex number a plus bi, let's see here, get Mathematica to make a nice long line about this. If we put a line above a complex number a plus bi, that stands for the complex conjugate of that complex number, and it's a minus bi. If b happens to be positive, so that the original complex number is above the real axis, then its complex conjugate will be below the real axis. The imaginary part will be negative. On the other hand, if b, the imaginary part of the original number, is negative, so that the original number is below the real axis, then the complex number conjugate will be above the real axis because negative b will be positive in that case. Anyway, watch what happens when you multiply a complex number times its complex conjugate. What do you get? Just go ahead and multiply it out. I'll leave it to you to check that you'll get a squared plus b squared. A real number, in fact, a non-negative real number. The outside and inside terms with the i's in them will cancel. You'll get negative abi plus abi, and those will cancel to give you 0 for the imaginary part. You'll get a real number, and in fact a non-negative real number. That observation allows us to be motivated to find a technique for dividing two complex numbers. Let's go back to the original example here. 5 plus 7i divided by 2 plus 3i. And the technique is to multiply by a disguised form of 1, and that disguised form of 1 is the complex conjugate of the bottom divided by itself. 2 minus 3i divided by 2 minus 3i. when we multiply these fractions by multiplying the corresponding numerators and then multiplying the corresponding denominators to get the new numerator and new denominator, in the new denominator you'll get a real answer. The i's will go away. First of all, in the numerator, FOIL it out. 5 times 2 is 10. 7 times negative 3 is negative 21, but you get an I squared to give you positive 21. You're going to get 10 plus positive 21, or positive 31 for the real part. If you don't believe me, or if you didn't follow that, go ahead and check it on your own. FOIL it out. For the imaginary part, you're going to get a 5 minus 3i is negative 15i, and the 7i plus times 2 is positive 14i. You're going to get a minus I for the imaginary part there, or the imaginary part will be negative 1 over something. And the something is going to be 4 plus 9, 2 squared plus 3 squared, 13. The final answer is 31 over 13 minus I times 1 over 13, or 1 minus 1/13 I. That's the final answer for the division. We did do that up here. We got that answer before, so we are illustrating that answer once again. And so this is a method. Again, multiply the top and the bottom by the complex conjugate of the bottom. That's always going to work to help you write your division in standard form. Let me add an extra step in here to begin with. This fraction is ultimately equal to this complex number, and yeah, more standardly we would write this in this way, and either put the I here or put it up in the fraction. Let me also say that because complex division can be thought of as multiplication by the reciprocal, that the equations up here relating the moduli and the arguments can be thought of in terms of complex division as well. Copy and paste these down here. What is the modulus of the quotient of two complex numbers as long as you're not dividing by 0? It would be the quotient, the ratio, of the moduli of the individual complex numbers. Initially thinking of this in terms of z1 times 1 over z2, you would think of it as the modulus of z1 times 1 over the modulus of z2, but that does equal this fraction here. And as far as the argument goes, maybe you want to guess it. What's the argument of z1 over z2, or an argument of it? One argument of that can be found by taking one argument of z1 and subtracting an argument of z2. The plus would change to a minus. So here, the product changed to a quotient, a division. Down here, the addition changed to a subtraction. So these two rules, as long as z2 is not 0, are the way you want to think about what happens with the modulus and the argument of a quotient.